Okay, so let's begin our today's session on Boolean algebra, and this is going to be the last session on this particular topic. Um, Here is a little glimpse of what we discussed in our previous class. We discussed the definition of Boolean algebra, and we saw that a Boolean algebra is a kind of abstract mathematical structure where a non-empty set is involved and three operations along with the additive identity and additive inverses are actually also considered in the structure. Sometimes they are written, sometimes they are not. So for example, in some books, you may see that this additive identity is 0 and additive multiplicative identity 1. These two identities are not mentioned in the structure. So in that case, you will find that the Boolean algebra is defined to be the mathematical structure consisting of a non-empty set and addition and multiplication operation along with the complementation. So you can say that this is a kind of quadruple structure. Or in some books, they specifically mention the additive identity and the multiplicative identity. So it is just a matter of choice and differs from author to author. We did this particular problem, exercise 1, and we also, as I promised you in my last class, that the duality principle that I didn't write in my earlier version of the note, I have introduced the duality principle over here. But before I introduce the duality principle, I gave the definition of a proposition. And what do you mean by dual proposition? Okay, so dual proposition, I have already told you, it's kind of proposition which when obtained by replacing one operation with the other and one identity with the other, and so on. And I introduced these two definitions over here just to explain the duality principle and its application in the proof of the theorem that I did in the board work in my last class. So if you have gone through the video, probably you've understood. And today also I can see the percentage of students is very poor. So you inform your friends to join as early as possible. So these are the laws which I explained in the last class. I did up to absorption law and left this theorem 3 for you to prove by yourself. And also I showed you that in exercise 2, how can we solve these examples, these types of examples, by considering the different theorems and the axioms in the definition to get into the result. I also told about two-element Boolean algebra, which consists of a non-empty set containing two elements, and a tabular version of the operation is written over there. Three operations are that you can see. One is called the Boolean sum, Boolean product, and Boolean complement. And one application of this particular two-element Boolean algebra is the switching circuit, which I explained briefly in my last class. Today I'm going to start from here, definition 3. And first of all, the first point that I want to make in this particular class is about the definition which is in front of your screen. It's a definition of Boolean variable. So what does it say? It says that in literal symbols such as x, y, z, x1, x2, dot, 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 xn, with or without subscripts, however you actually name it, doesn't matter, used to represent an element of B01 is called a Boolean variable. Okay, so Boolean variable, to represent a Boolean variable, you can actually use any symbol of abstract nature. It doesn't have to be always 0 and 1. So for example, if I consider this set B, and if I replace 0 by x and 1 by y, and if I explain the same operation that I explained above, a two-element operation that explained in the table above, then also it will work out. So in this case, if I replace 0 by x, so in the plus operation we'll write x plus s equal to x, and y into y equal to y, like this. So we can replace these notations 0, 1 with the notations x, y, z, and so on. Okay, because sometimes you have to deal with many such complications that it is wise to use these abstract notations to define the variable. Now, in terms of the variables, we can define a Boolean expression. Very trivial Boolean expression is 0 and 1. But if I consider in general n number of notations like x1, x2, xn, then these notations can also be treated as Boolean expressions. In general, if alpha is a Boolean expression, then alpha complement is also a Boolean expression. And if two Boolean expressions are present, then their product and their addition also represent a Boolean expression. These are very basic mathematical fact that you can introduce in the topic of Boolean algebra. Okay, and as I have numbered these properties from A to D, I have written over here that only those expressions which are determined by the rules defined in A to B to D are Boolean expressions in the terms of x1, x2, xn, the new set of variables, which are actually called the Boolean variable. Any function of this Boolean variable is denoted by alpha of x1, x2, xn. It's called Boolean expression, or sometimes it is also known as Boolean function. And you can see that it is a multivariable function because here the function is alpha and its inputs are, there are n number of inputs inside it. Okay, so this type of things are actually, you can call a multivariable function. So it is this is a Boolean expression or Boolean function that I have defined over here. Now the point is, when we can consider two Boolean expressions. If I consider two Boolean expressions like this, one is denoted by alpha x1, x2, xn, and beta is another Boolean expression of same nature. Beta is another Boolean expression of same nature. Then, I mean, the input variables of beta are same as that of alpha. When do we say that alpha and beta are same? Now, alpha and beta, these two Boolean expressions will be same, will be called equal if they assume the same value for every possible assignment of values 0 and 1 to the variables x1, x2, xn. So this equality of two Boolean expressions that I'm going to explain to you with an example. I have considered the example over here, which is called, defined in exercise 4. We have been asked whether these two Boolean expressions, one is alpha of x1, x2, which is x1 plus x2 complement, and another is beta of x1, x2, which is x1 complement into x2 complement. Are these Boolean expressions equal? So I'm going to show this calculation here. And for simplicity, you can use this ordinary plus symbol in place of this plus symbol, and ordinary dot in place of this cross. Okay, that particular matter has been explained to you in the previous class. So I'm going to explain how to show that these two expressions are equal or not, and whether they are indeed equal or not. So I'm going to write it over here. So for this, what we need to do, we are going to formulate two different tables. One table is for the function alpha, and we will consider the two variables x1, x2. These are called the Boolean variables, and each of these two Boolean variables will consider the elements 1 and 0 each. So what are the possibilities? The possibilities are 1, 0. So let us start with 1, 1, 1, 1, 1, 0, 0, 1, and 0, 0. Okay, these are the possibilities. And if I try to add these two numbers, these two variables, keep in mind that we have to consider the operation, two element operation that I explained in the previous page, that 1 plus 1 becomes 1, 1 plus 0 becomes 1, 0 plus 1 becomes 1, 0 plus 0 becomes 0. I'm referring you to go back to the two element Boolean table that I made, two element Boolean table operation that I discussed in the previous page. So with respect to this operation, we have got this, and we need x1 plus x2 whole complement. This is our requirement. So we can introduce one another extra column. So we can write it as x1 plus x2 complement, and you know that one complement is 0. We proved it in the last class, and one complement is 0, one complement is 0, and 0 complement is 1. So this chart that we have obtained is the chart for the Boolean expression alpha. Similar type of problems you have done in mathematical logic, so I hope you are not facing any trouble to understand the concept. Probably you have understood what I need to show. I need to show that this particular expression, this particular function beta should have the same column as that of x1 plus x2 whole complement that we are going to check. So let's start. So now we are considering beta, and again then we consider the two variables x1 and x2. The possible values are 1 1 1 0 0 1 and 0 0. And what we need x1 complement multiplied by x2 complement. So first of all, we need the column for x1 complement, and then we need the column for x2 complement, and then we need the column for their multiplication, x1 complement into x2 complement. Now you go back to the chart of operation of multiplication that I explained in the previous page, from which we can deduce that 1 into 1 is 1 into 1 becomes 1 into 1 not 1 into 1, x1 complement. Since x1 is 1, so it becomes 0. Since x1 is 1, it becomes 0 1 1. These are the things. And for x2 this is x2, huh? Okay, so this x2 complement becomes 0 1 0 and 1. And then you multiply x1 complement multiplied by x2 complement. So by the multiplication table of two element set, 0 into 0 becomes 0, 0 into 1 becomes 0, 1 into 0 becomes 0, and 1 into 1 becomes 1. Now you just highlight them, and you see that this and this have the same representation. And therefore, by this definition 5, this Boolean expression and this Boolean expression, they are equal. Okay, so this is the way by which you can, just like this type of problem is just like the problem we did in the mathematical logic, where we used to show that two statements are equivalent. We used to prepare the truth table for one statement and truth table for another statement, and then we just compare the last column of the truth table. Same thing has been done over here. Sometimes in some book, author in the two element set or two element Boolean algebra, the author also use a symbol as I have said, that you can use the symbol like x1 x2 dot dot at x. And what does it mean? You can consider the this variable. This is a kind of statement, and this is a kind of statement, and in place of 1 and 0, you can also use T and F, truth and false. Okay, but this similarity is not a kind of magic. This similarity comes because I already told you in the beginning, in the monologue of my previous lecture, that this Boolean algebra came into existence because of George Bool's philosophical treatise on laws of thought. So therefore, this sort of similarity between the propositional logic and Boolean algebra is quite obvious. Okay, so basically we are treating same thing from two different perspectives, you can see. Ultimately, they will converge on a single point. Okay, so anyways, let's proceed. So I leave this particular problem exercise 5 for you to solve by yourself. Here you are just going to find this big expression in mathematical. You are going to prepare a table, a chart for this. Okay, and you can compare the final column. Final column will be x1 plus x2 into x3 complement. I do not have the answer. I haven't provided the answer. So if you want the whether your calculation is right or wrong, uh, in two ways that can be done. Either you can text me your answer, I'll later check, or you can circulate your solutions among your peers, and each one of you can check others solution, and you can thus verify whether your answer is correct or wrong. Okay. Okay, so then, and now this, in terms of these Boolean variables, I can restate the properties in the following manner. So for the time being, I'm going to stop sharing the screen and I'm going to write the properties in the whiteboard. Uh, so if we have these Boolean variables, then, for example, we consider a set of Boolean variables as follows. We can consider a theorem that you don't have to prove it, but you just note it down somewhere. So let x, x1, x2, x3, these be the Boolean variables. These be the Boolean variables. Then the following properties actually hold. First property is called the commutative property, which states that x1 plus x2 is equal to x2 plus x1, and x1 into x2, x2 into x1. See, I'm actually simplifying things. I'm not using the sign which I used for addition and multiplication to just save the time. Now, in this particular theorem, we are going to introduce the associative property also, and for which I'm going to write x1 plus x2 plus x3, which is similar to x1 plus x2 plus x3. And not only this, with respect to multiplication, that needs to hold also. So we are going to write it as x1 into x2 dot x3. This is associativity property. Try to recall that in the previous class, we didn't introduce associativity property in the definition of Boolean algebra. Rather, in the theorem, we, as a statement, associative property were actually mentioned. I asked you to do the theorems proof by yourself. Distributive property goes like this. This is the distribution of multiplication over the addition of two numbers. We are quite familiar with this sort of things from our since our childhood, but we are not familiar of this expression. It is kind of atypical, as I mentioned in the previous case, but you have to know that in Boolean algebra, this type of thing happen, and we can write it in the manner I have written. And in 4, we can introduce the idempotent law, which states that x1 plus x1 is equal to x1, and x1 into x1 is equal to x1. Then you can introduce the identity law. The identity law is as follows: x plus 0 is equal to x, and x into 1 is equal to x. We are quite familiar with this identity law, but inverse law is quite atypical. As I discussed in the previous case, here x plus x inverse, here I mention x complement by x prime for simplicity. So x plus x prime will not be 0, it will be 1, and x into x prime will not be 1, it will be 0. And there is another law which I didn't provide any name for that, but right now I'm going to provide a name, but you know that this is there. It is called dominance law, and we proved this dominance law in the one part of the dominance law were proved in the previous class, which is this one: x plus 1 equal to 1 and x into 0 equal to 0. Absorption law you know very well, so let us not highlight it because we already discussed absorption law. Absorption law goes like this: So we can write x1 plus x1 dot x2. This becomes x1, and yeah, these are together, and x1 dot x1 plus x2. This is another form of absorption law, which is x1. And number 9 is De Morgan's law. We are quite familiar with De Morgan's law. These are x1 plus x2 whole complement is equal to x1 complement into x2 complement, and x1 x2 whole complement is equal to x1 complement plus x2 complement. Kind of atypical, but if you think of set theory, you will find that this happens because A intersection B complement is equal to A complement union B complement, and A union B whole complement is equal to A complement intersection B complement, where union plays the role of plus and intersection plays the role of multiplication. And the last 10th property, you can consider the double complement law, which is very simple, which states x complement of complement is equal to x itself. So you see, so far that we have learned in our previous example, in theorems, in definitions, all these have been jotted down over here in terms of the Boolean variables. It's a kind of revision for you to go through the properties once again, and those who actually missed my last class, this is a kind of thing that they need to know. Okay, so you have to jot down, you have to take the screenshot of this particular page somewhere, and it will be helpful for you to solve the problems sometime. Then I'm going to introduce another definition, which is also very important. These definitions which I have not yet introduced in my note. I'm preparing the note still, and I will introduce these definitions in due time. The definition is this: let alpha be a Boolean expression. The alpha is a Boolean expression, a Boolean expression beta. The Boolean expression beta is said to be the dual of alpha if beta is obtained from alpha by replacing each occurrence of Boolean sum by Boolean product. Or Boolean product by Boolean sum, or 1 by 0, or 0 by 1. If beta is a dual of alpha, then we write symbolically, we write beta to be the dual of alpha. So we write symbolically like this. Whenever you find a kind of thing like this anywhere, that beta equals to alpha d, don't think that alpha has been multiplied d times with itself. This expression means, in Boolean algebra's domain, this expression means that beta is the dual. This d stands for dual. Beta is the dual of alpha. Okay, for example, let us consider the Boolean expression alpha is equal to 1 plus x1 dot x2 dot x3 prime. Now, if I ask you, what is the dual of, suppose I'm asking, the question is, find alpha d. So what will be your answer? Your answer will be, the alpha d will be, first of all, you are going to replace 1 by 0. Then you are going to replace plus by dot. Then you are going to put a bracket, and inside the bracket you are going to replace dot by plus. Put another bracket like this. Here the dot will be replaced by plus, and this x3 complement will remain same. And you can call this to be your beta. So this type of expressions you can very well understood regarding sorry, a WhatsApp message came. This type of example you can face in the online examination, like they may ask you several expressions to, and you are going to choose which expression is the appropriate dual of a given expression. Okay. And also you have to know this particular result, that if for any two Boolean expressions, alpha and beta, if alpha equals to beta, then the dual of alpha and the dual of beta, they are also same. It can easily be proved. Okay. So this is the thing that you have to know quite well. And probably if you are thinking that what is happening over here, some abstract scenarios are being played, abstract things which seem very irrational to us sometimes. It means you may be right. They seem very irrational, but what is the most important point is that whenever you are doing kind of Boolean algebra with your things, then you have to keep in mind that I have this works that I can work with. I have to be in the domain of this. I have to be in the space of this Boolean algebra, and there I can, with the set of rules, I can do things. These rules, and again I'm saying, becomes significant when you use them to find various circuits and gates for algorithms. Then you will try to find out that you will be able to understand what is happening. But whenever we are going to design a circuit, whenever you are going to build a kind of gate, then you have to apply these rules and over there to build to build the same. Okay, you cannot your circuits, your gates shouldn't break the Boolean rules, and it is well defined. Now let us come to the next definition. The next definition is saying that let capital B be a two-element Boolean algebra and let x1 x2 dot 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 xn be a Boolean expression, then the corresponding function, f alpha is a function f alpha from Bn to B defined by f alpha b1 b2 bn, which is equal to alpha of b1 b2 bn for each n tuple b1 b2 bn belonging to bn. So this is the expression. This is another important definition, which is very fundamental to Boolean algebra. It is saying that you are going to consider, as you have come across the notation like Rn in the study of vector space, you know that Rn is similar to taken a set of real numbers n times. Okay, so this sort of expression we use to denote that the element which belongs to Rn. So if I write y belongs to Rn, then y can be expressed as the coordinate system as follows. So here also we are considering the expression B, which is a Boolean algebra, and we are considering Bn, whose element will be of the form B1, B2, Bn, as I have mentioned over here. And when we consider these type of elements and we apply the function f alpha, it gives us a Boolean expression. It means f alpha of b1, b2, bn is equal to alpha of b1, b2, bn means if we consider n tuple from bn and we apply the function f alpha, then that f alpha gives us a Boolean expression. Not every f alpha gives us a Boolean expression. Or is it so? It's a question whether every function is a Boolean function or not. That is a matter of, study. I have activated the chat box. You can put your attendance over there. Okay, now I'm going to discuss this example. Suppose let alpha x1, x2, x3. Please put your attendance in the chat box. Alpha x1, x2, x3. This is a Boolean expression which is given by x1 plus x2 complement into x3. Suppose this be a Boolean expression. This Boolean expression, and in three variables, x1, x2, x3. Okay, then the corresponding Boolean function, f alpha, which is a function from Bn to B, is suppose defined by f alpha of b1, b2. Okay, so here the one modification, since I have considered this triplet kind of thing, so we can consider b3 over here. We can consider n equal to 3. So we considered an element which is of the form b1, b2, b3, and this is going to be a Boolean expression alpha b1, b2, b3, which is b1 plus b2 prime dot b3. See, in this variable, in this Boolean expression, we have replaced the three quantities x1, x2, x3 by b1, b2, b3. And it is going to be true for all b1, b2, b3. belonging to capital B3. The function f alpha can be expressed as follows in tabular form. So we can write it as x1, x2, x3. These are the three variables, and you know what are the possibilities. If I consider this, then the possibilities will be 1, 1, 1. This is one possibility. 1, 1, 0. This is another possibility. 1, 0, 1. Third one. Fourth one is 1, 0, 0. 0, 1, 1. 0, 1, 0. And two more, I think. Okay, then 0, 0, 1. And please tell me if I'm missing anything anywhere. And last one will be 0, 0, 0. Okay, so these are the I can see 29 participants, but only 20 participants have so far written their roll numbers in the chat box. Anyways, then I can apply quickly the my alignment is not good. So you just make your alignment accordingly. How many? Four things are there, and alpha can be written as, what is your alpha? Your alpha is x1 plus x2 complement dot x3. So if I apply the multiplication rule, this will be 0, 0, 0, 0, 0, 0, 1, 0. And f alpha of x1, x2, x3 is nothing but this one. 0, 0, 0, 0, 0, 0, 1, and 0. So this is the thing by this here in this example, what I am showing, trying to show that you can define a function with the help of a Boolean variable, and these functions are actually the way by which these functions are actually made. This has been demonstrated in front of you over here. And the values, as you can see, this itself is a kind of function, Boolean expression. This is itself a Boolean expression, which is given by the following formula. And not only this, these Boolean expressions is having the values like 0 and 1. Okay. For this example, it is 0 and 1. Several zeros are there. Only one is present. But in other cases, the cases may be different. And all these values are the functional values corresponding to the Boolean function that we have defined over here. At this stage, I am stopping. The next session, I'm going to explain the DNF and CNF, which is the last topic of Boolean algebra. So I'm stopping here right now.